Okay, so welcome everyone to the first One World seminar after our break. So we're very happy to have Hemant Tyagi speak this week. So Hemant did his PhD in 2016 from ETH Zurich. He was then a research fellow at the Andre Institute in Edinburgh for 2 years until 2018. And since 2018, he's been a researcher at INRIA Lille. We're very happy to have him this week talking about dynamic ranking and translation synchronization. So it's over to you.
Okay. So thank you for inviting me. So I'm going to be speaking about today a problem which is related to statistical learning on graphs, and that's something I've been working on for the last 4 or 5 years quite extensively. So in particular, I'll talk about something that I'm really interested in these days, which is for learning dynamical processes on dynamical networks. And this is just part of that project. So this thing that I'm going to talk about is joint work with my former PhD student, Eglantine, who graduated just last week, and my postdoc, Ernesto, who is now in Munich. Okay, so I'm going to talk about essentially ranking and translation synchronization, right? But the bigger picture is statistical learning on graphs. So what does it mean? Well, typically in many applications, we are often given data that involves pairwise comparisons between a collection of n items. Okay, and I'll give examples to show what this means. So when we're given this pairwise data, we can actually model this as a graph with n vertices, and where the edges denote the pairs of items that are compared. Okay. And the nodes of the graph have a latent signal that we wish to estimate from these pairwise, this pairwise information. So the goal is to estimate this latent signal residing on the nodes from the pairwise comparison data. Okay, like that's a typical abstract formulation of this problem. So here's the first example, which is perhaps the most popular example for statistical learning on graphs, which is clustering, okay, or also known as community detection. So here the graph, we are given a graph, right? And the graph really encodes pairwise similarity information between the nodes. Okay, so if there's an edge between two nodes, it means they are friends. If there's no edge, it means, well, they don't know each other. And the edges can also have weights, etc. But the goal is, given the graph, you want to find a partition of the graph into these dense subgraphs or clusters, okay, or cliques, such that there are very few edges between the clusters. Okay, so each subgraph is very dense, a lot of edges, and there are very few edges across connecting to different subgraphs. And it has many applications in social networks, biology, finance. And this is really very well illustrated by this figure that I stole from the survey of Emmanuel Abbé. So typically the graph that we are going to be given is going to look, I mean, it's essentially the graph on the left-hand side, okay? But just by looking at the graph or the adjacency matrix, we cannot really make much sense of what the latent structure of the graph. But what we would like to do is to untangle the graph and to recover, hopefully, I mean, if this is indeed the case, recover something like on the right-hand side, where you discover these latent communities. And in this case, you have 5 communities which are very densely connected within them, and there are very few edges connecting different communities. Okay, so in this case, the problem would be, given the graph, find a partition of the graphs into these latent communities. And of course, the hypothesis is that there indeed exists such a latent partition, right? I mean, in general, if you're given the complete graph, then there's nothing to do. I mean, there's just one big clique. But the interesting case is, and this happens in many applications, that a lot of times the graphs that we encounter, they have this latent structure where they can be partitioned into these K dense communities or dense clusters. So the goal would be to, given the graph on the left-hand side, detect these communities or color them on the right-hand side. So in this case, the node signal, you can think of it as this membership vector, this Boolean vector, which is 1, 0, which denotes the membership of that node. Okay, so indeed, you are actually estimating this latent signal of the node given the pairwise information. Is this fine? And please feel free to stop me if you have any questions. Okay, so that's the first example. And the second example, which is really what I'm going to focus more on in this talk, is ranking. So here you have n items, and the pairwise information is of the following form. So it's of the form item I preferred over item J, or item I beats item J. Okay, so you're given this pairwise comparison between I and J, and then you're given information of the form I beats J or I preferred over J. And given this pairwise information, the goal is to recover the latent ranking of the items. Okay, so it has, again, applications in sports, tournaments, recommender systems. For example, if you look at the figure on the left-hand side, so here you see that, okay, there are some nodes, and each node is represented by a movie. And this direction of the arrow denotes which movie is preferred over which movie, right? So for example, if you compare Avatar and Titanic, and perhaps this is my own internal preference, so I would maybe prefer Avatar over Titanic. So the arrow points from Titanic to Avatar. So when Titanic and Avatar were compared, I preferred Avatar. So Avatar beats Titanic, right? And similarly for the other nodes. So you can think of an application of this in the context of recommender systems. For example, if you go to IMDb, I mean, it would typically want to learn the internal preference of movies for a user, like for me. So to learn that, it might perhaps show me pairs of movies and ask me to choose which one I prefer, right? And so if it shows me these 5 movies, and it then, I mean, it shows me maybe Avatar and Titanic as a pair, I would prefer Avatar. If it show me Le Perrin and Moulin, and I would prefer maybe Le Perrin, etc. So by showing me these pairs, it would hope to get a pretty good idea of what kind of movies I like. I mean, do I like thriller movies over drama, etc.? And then by learning this internal preference, it would then recommend to me like this list of 10 movies, which it hopes is a pretty good guess of the type of movies I like, the genre of movies I like. Okay, so that's like one example. And also in sports tournaments, like for example, if you have like the FIFA World Cup, you have some collection of teams playing, and then you have these outcomes. For example, if Argentina played Spain, maybe Spain beat Argentina, and so on and so forth. And then given these pairwise outcomes, you would like to maybe recover the latent ranking of the teams. Okay. And of course, I mean, as a sanity check, the problem in real data is that you have a lot of inconsistencies. So, for example, you can see here that Spain, France beat Spain, Italy beat France, and Spain beat Italy, right? So there's a cycle, I mean, a directed cycle, and you cannot, I mean, okay, so you cannot just traverse the graph and hope to recover the ranking by some naive methods. I mean, you need a method which is robust to all these inconsistencies. That's like an important part of this problem. Okay. Now, if you want to study these in a principled way, in a mathematical way, so in statistics, what one does is we formulate a statistical framework to study such problems, which essentially means you consider a stochastic generative model for generating the pairwise data, where the latent signal is kind of planted. It's a ground truth. Okay, so we assume a stochastic generative model which generates the pairwise data with the planted latent signal, which has to be estimated. And having such a statistical model is not artificial because it really provides a setup, a very principled setup for evaluating the performance of any algorithm. I mean, not only theoretically, of course, but also empirically. So if you design a method, it provides a really nice playground to evaluate your method against other methods, where you have this well-defined ground truth and you can really calculate the estimation errors and evaluate the performance of algorithms, right? So a stochastic generative model is really important. And so just coming back to the example of clustering, the stochastic block model is something most of you might have heard of, the SPM, which was devised in 1980 by Holland. And it's a very, very classical model, which actually is still being studied to this date. There are thousands of variants of this model, but the precise minimax rates, estimation rates for the SPM were actually only resolved, I mean, perhaps 8 years ago. So it's not that easy. And the model says the following. So you have a latent partition of your graph into K communities. Of course, the algorithm doesn't know this. So there's a latent partition in C1, C2, CK of the graph. And then we consider a connectivity matrix P, which is a K by K probability matrix. And then we generate the adjacency matrix A as follows. So for each I and j, where I belongs to community K and j belongs to community K prime, we generate Aij as a Bernoulli with parameter pkk prime, pk comma k prime. Okay, so typically A, if you look at the expectation of A, it will be low rank or approximately low rank, rank K. And the point is, given A, can you estimate these latent communities? And there are lots and lots of methods to do this. I won't go into the details, but it's just to give you a flavor of what exists for clustering. But my focus is really on ranking. So let's from now, let's just focus on ranking. So for ranking, perhaps the most classical stochastic generative model is the Bradley-Terry-Luce model, which was devised independently, I think, by Bradley and Terry and Luce separately, I think. And the model is the following. So it's a parametric model. We consider a latent strength vector, W star, which is a vector of length n, and where Wi star is the latent strength of item I or node I. Okay, and all these strengths are strictly positive, and we are given an undirected comparison graph G, okay, on these n items with edge set E. And now we generate the pairwise comparisons as follows. So if you denote Yij star to be the probability that J is preferred to I, then we define this probability using these latent strengths as just the ratio of Wj star over the sum of the weights, Wi star by Wj star. Okay, so define this for each I not equal to j. And then we generate the pairwise comparisons as simply these independent Bernoulli. So for each ij in the edge set, you generate these L independent or LIID Bernoullis with parameter Yij star. Okay, so L is just like this parameter which controls the number of comparisons, because maybe two teams or two items were compared independently by L judges. So you have these L outcomes, and all of them are IID from the same Bernoulli distribution with parameter Yij star. Okay, and so you're given this information for each ij in your edge set. Okay, so for each ij, you're given these Bernoulli outcomes, L Bernoulli outcomes. And now, if you're given these Bernoulli outcomes, then actually you can calculate the fraction of times j beats I, which you will denote by Yij, right? And so Yji is just 1 minus this fraction. And actually, this is a sufficient statistic. So we don't care about these Yijls. You can just calculate the fraction Yij, and this is a sufficient statistic. So if you write down the ML, if you write down the likelihood function of this model, it will completely depend on only the Yij. So it's a sufficient statistic. So we can just care about the Yijs. Okay, so the data that we are given for each ij is the fraction of times I beats or j beats I or I beats j conversely. So given the graph and given for each edge in the graph, the fraction of times I beats j, the goal is to recover this latent signal W star. Okay, so recover W star given the graph and the pairwise, this pairwise data Yijs. Now, here's a couple of sanity checks, which you can see from here. You can only recover W star up to a global scaling, positive scaling, right? Because if you multiply W star by some scalar alpha, the probabilities are unchanged. So these Yij stars are unchanged. So it's only well defined up to a global scaling. So that's one thing. The other thing is that G needs to be connected. Right? So because if G is not connected, then you have these two disconnected components, and there is no comparison between an item in one component and the item in another. So you cannot hope to resolve the ranking between these two components, right? So G needs to be connected. So these are two sanity checks that one has to keep in mind in order to be able to prove any theorem or anything meaningful. Okay. So what is known? Well, a lot of things are known, but I'm going to focus on something very specific. I mean, this model has been studied to death. There are lots of results for different types of graph topologies. But I want to focus on this very particular method known as rank centrality, which is a spectral method and which was proposed in 2017 by Negaban, Siwong Oh, and Devarat Shah. A very elegant method which proceeds as following. So given this pairwise data, we construct a random walk on the graph. Okay, so this random walk has this transition matrix P hat, which we construct, and P hat is defined as follows. So for each edge ij, your P hat ij is really Yij scaled by the maximum degree of the graph. Okay, so you just put the fraction of times whatever I beats A or J beats I for the ijth entry, and you do this. And then for the diagonal entries, you simply make this P hat a transition matrix, so it needs to be row stochastic. You simply set it to be 1 minus the sum of the entries of the row. And if ij was not compared, you simply put 0. So P hat is actually just a transition matrix for a Markov chain. I mean, that's clear because D max is the maximum degree of the graph, right? So each entry P hat ij for ij belonging to the edge set is between 0 and 1. And the sum of the entries in a row is 1. So it's row stochastic. Okay, so it's a transition matrix for a Markov chain. But why do we do this? I mean, what is the point of making this Markov chain? Well, now I claim that you can actually just compute the stationary distribution of this Markov chain induced by P hat. And this is a good estimate for your latent strengths of the items. So it's very simple. You compute you construct P hat, find the leading left eigenvector, which is the stationary distribution of this Markov chain, and then this pi hat is a very good estimate of the latent the strength vector W star. I claim that, and why is this the case? Because if you were to look at the population version of this transition matrix, so expectation of P hat, it turns out that if the graph is connected, then this quantity pi star, which is W star normalized by its L1 norm, so pi star is a distribution. So pi star is actually the unique stationary distribution of the population version of P hat if G is connected. And why is this the case? Because if G is connected, then this Markov chain induced by expectation of P hat is irreducible. Right? So it has a unique stationary distribution. It's also aperiodic, it's also reversible, etc. So it's very well defined, this expectation of P hat, right? Because keep in mind that if you were to compute expectation of P hat, you would see that for all ij's belonging to the edge set, all these entries would be strictly positive. Okay, so whenever you have an undirected edge between I and j, and if you look at expectation of P hat, you would have an edge from I to j and also an edge from j to I, and both these edges would have non-zero weights. Okay, so this Markov chain is irreducible. It also has self loops, so it's it's aperiodic, etc. It's also reversible. So pi star is the unique stationary distribution of the population Markov chain if G is connected. And so if this is the case, then you would maybe expect intuitively that, okay, if pi star is this stationary distribution of the population matrix, but I observe not the population matrix, but the empirical version of the matrix, and I would expect maybe intuitively that perhaps P hat will concentrate around expectation of P hat, so maybe pi hat will also concentrate around pi star. And again, just as a sanity check, note that we are going to estimate pi star, right? Because we cannot, W star can only be defined up to a global scaling. So here pi star is normalized. So it's W star normalized by its L1 norm. So we cannot estimate W star, it's not well defined, but clearly pi star is well defined. So we're going to estimate pi star. And intuitively, this makes sense because you might expect intuitively that P hat is close to its population version. So maybe pi hat should be close to pi star. But showing this precisely, it's not easy. And in fact, showing the right rate is not easy. And I want to mention the state of the art for this problem. So which was shown recently by Yuxin Chen and others. I don't remember their name, and also Chao Gao and others who improved the result of Yuxin Chen. And the result says the following. So this result is specifically for an Erdős-Renyi graph. So if your graph G is an Erdős-Renyi graph with parameter P, and an Erdős-Renyi graph is simply a graph where each ij is a Bernoulli random variable with parameter P, and all the edges are IID. So if your graph is a random graph, an Erdős-Renyi graph, and your P is greater than log n over n with a suitable constant so that the graph is connected, then with high probability, you have this L2 error bound and L infinity bound for estimating pi star, and everything is non-asymptotic here. So, and this high probability is roughly 1 minus n to the minus 10 or something like this. So it's a really high probability. So you have this L2 error rate, right, which is 1 over square root of NPL. And you also have this infinity error rate, which is the same, but with a log n factor. So square root of log n NPL. And in fact, both these bounds are optimal. So and these bounds are optimal for the up to constants, at least for the spectral method. And in fact, similar bounds exist for the maximum likelihood estimator. Okay, and these bounds are optimal. And if I remember correctly, for the MLE, perhaps it's optimal up to a constant as well, if I'm not mistaken, but perhaps it's not the case for the spectral method. But anyway, if you forget constants, these rates are optimal. So what do these bounds tell us? Well, first they say, I mean, something very intuitive, right? So if L increases, your error your error decreases, right? So this is something we would expect based on what we said here, right? So for each ij, if you have more and more comparisons, I mean, you will be more and more close to y star ij. So I mean, your error should decrease. But also the error decreases if n times p increases. And n times p is really just the expected degree of an Erdős-Renyi graph. So what it says is that if the expected number of comparisons increases, then your error decreases at this 1 over square root n rate, which is the parametric rate for this problem. Now, one thing I want to mention is why do we care about, I mean, the L2 error bound is a bit weak, right? If you want to recover the ranking of the items, what would you do? Well, you would hope to estimate the latent strength vector W star. And if you estimate it well enough, then from your estimate W hat, you would want to just sort your strengths and just recover the ranking in the natural way. But to be able to recover the ranking globally, you really need an L infinity bound, right? Because if you really want to recover the latent strengths, but in the L infinity norm, and if your L infinity error is small enough, in particular, if it's smaller than the minimum separation of the strengths between two items, if you drive your error, for example, below half the minimum separation, then if you were to sort your estimated strength vector, you would actually recover the global rankings exactly. Okay, so the L infinity error control is really important to do that. Okay, so from this L infinity bound, you can actually deduce how large this quantity n times p times L needs to be able to recover the latent ranking exactly. Okay, it's a discrete problem, right? Because you want to recover the rankings. It's a discrete problem, so you can actually do it exactly if you have enough comparisons. So this is the state of the art for Erdős-Renyi graphs. So the message is that for Erdős-Renyi graphs, the spectral method and the MLE are both optimal. And if I remember correctly, the MLE is even optimal up to the constant. So this is it for static graphs. This is what I want to talk about. The static case when you just have one comparison graph. I mean, if there's any questions, feel free to.
You might be about to answer this next, but I mean, are there similar results on different types of graphs, particularly like geometric graphs?
Yes, there are results for other types of graphs. And the question is whether, and the thing is in general, of course, the connectivity of the graph and all these results, I mean, it appears in the bounds. For example, in terms of the Fiedler eigenvalue of the Laplacian or other notions of the connectivity. I'm not sure if optimal rates, like if there's a particular theorem which is optimal for all types of graphs, I'm not sure if that's the case, because you really need, there's some specific knowledge of the graphs is needed to be able to obtain sharp rates. For example, when you have this Erdős-Cheney, nice homogeneous Erdős-Cheney model, it's really important in the analysis. I mean, if you had an inhomogeneous Erdős-Cheney graph with Pij probabilities, I'm not even sure. I mean, some things will change. There are some simplifications that happen in these analyses, which I would say changes. So it's a bit tricky when you have general graphs, but there are results known for general graphs. I'm just not sure if you, and perhaps for some of those graphs, you have optimal rates, but I'm not sure if you have like optimal results for all types of graphs. I'm not sure. But I should say that there are lots and lots of papers for the BTL model, even though it's very unrealistic in practice. It's a parametric model. There are much stronger models which are known, like non-parametric models by Niharsha and Wainwright. But still, it provides a nice playground to do analysis. So, and as you can see, these results are quite recent, so it's still an active area of research. Okay, so there's nothing else, I'll move forward. So this is it for the static case. And now my interest, and this is something I've been really interested in for the last 2-3 years, and I'm still interested in, is for the dynamical setting, right? So what can you say about the dynamical setting when you have a time series? So clearly, many times in practice, the data is time evolving, right? For example, in sports tournaments, I mean, the FIFA World Cup comes every 4 years. So, I mean, if you look at all the FIFA World Cups in the past, you have a time series of soccer competitions. So what happens here is that you have a sequence of graphs, G0, G1, G2, up till GT. Okay, so for each, you have these discrete time points, 0, 1, 2, 3, 4, up till T. At each time point, you're given a graph. So when the FIFA World Cup happened, for example, in 2018, there was a graph there. And then you have the pairwise information corresponding to that graph at that time point. Okay. And now, if you're given this sequence of pairwise information, so you're given a sequence of graphs, and for each graph, the corresponding collection of pairwise information, the goal is to estimate the latent ranking at any given time t. And this time t need not necessarily be a grid point. So because you assume that the model is evolving, the latent strengths are evolving in a continuous manner. So actually this time t could be between 2 grid points as well. Okay, so the goal is to estimate the ranking at any given time point t. So point-wise estimation perhaps. Now, what is the sanity check here? I mean, what is the difference between this and the static problem? Well, if I were to estimate the latent ranking in 2018, for example, based on, the FIFA World Cup, based on the pairwise information in 2018, I could, as a sanity check, just look at the data in 2018 and just apply what I described to you in the previous slide, right? So I could just use any static method and apply it for that particular time point. But of course, okay, you can do that, but this would not work if all your graphs were very sparse, impossibly disconnected. And this could happen. Maybe your graphs are possibly disconnected. So this would not work. So whenever you have a time series or something evolving with time, I mean, the sanity check is always that you want to really, if you want to do point-wise estimation, you want to really leverage information over time to perform point-wise estimation. Okay, so and of course, how you do this leveraging depends really on your model for evolution. But that's a sanity check, right? So we really want to leverage information over time to do point-wise estimation. And somehow you should do better and better as you have more and more temporal data. And I will make this precise in the coming slides. So that's really the sanity check whenever we have a dynamical model. Okay, but of course, clearly, I mean, you need to have a well-defined evolution model to be able to do something meaningful. I mean, if you want to leverage information over time, you really need to have a well-defined evolution model. I mean, information between the data needs to be shared over time so that you can leverage it over time to do better and better as you have more and more data points over time. That's the sanity check. Okay, but even if all your individual graphs were connected, I mean, the point is that you can still do something by just doing estimation by looking at by applying a static method on that particular time point. However, again, the same philosophy applies. You can still hope to do better than that by leveraging information over time. So really making use of the temporal nature of your data. So these are two sanity checks. Is this clear? So it's important. I mean, we really need to ask what is the point of even looking at a dynamical problem? I mean, it's really this. Okay. And what we did is kind of simple. So we introduced this non-parametric dynamic BTL model. I mean, we really didn't introduce it because it was also introduced just at the same point by Bong and others. But yeah, so this model is very simple and it says the following. Assume at each time t that you have the strength vector WT star of length n. So you have n items. The number of items is the same over time for simplicity. And WT star I is the strength of item I at time t. And I'm going to focus, I'm assuming my time domain is the 0-1 interval, which is without loss of generality, just as we do in non-parametric estimation. So time is limited to 0-1. And this is the strength vector. WT star is the strength vector at time t, and WT star I is the strength of item I at time t. And then you can just have a BTL model at time t. So the probability J is preferred to I at time t is really the ratio of these strengths, which we will denote by Yij star of t. So you just put a t in whatever we saw just now for the BTL model. Okay, so you have these pairwise probabilities, which are functions of time now. But the data is given to us at discrete time points. So consider a uniform grid calligraphic T, which has T plus 1 time points. At each grid point, we have a graph GT. So we have these T plus 1 graphs, sorry. And at each grid point, T prime, I'm given these pairwise outcomes, Yij of T prime, which are generated from the BTL model at that point, grid point T prime. Okay, so we just have a sequence of BTL models at each grid point. And each BTL model is defined by GT prime and the strength vector WT star prime. Okay, but we cannot stop here, right? We need to have something meaningful. And I'm going to assume that the data is independent over time. It's not realistic, but it's I mean it's like it's still a non-trivial thing to consider as a first step. But these models are not arbitrary. We're going to assume that these models are smoothly evolving with time. So we have this Lipschitz smoothness assumption, which says that for any ij, this Yij star of t, which is a univariate function of t. So the pairwise, the probability of I beating j or j beating I is a smooth function of t, and we assume it's a Lipschitz function of t. Okay, so if t and so at two time points which are close to each other, these probabilities are not going to be too far apart. Lipschitzness can be relaxed to a Holder continuity assumption. It's not important. Everything will work. So yeah, but what we say is that the data is your model is smoothly evolving over time. So you have a BTL model at each grid point, but the BTL model is smoothly evolving, which really means that your pairwise probabilities are smoothly evolving. Or equivalently, your strength vectors up to some normalization are smoothly evolving functions of time. Okay, so given this, the goal is the following. For any given t belonging to 0, 1, and this t need not lie on the grid, we would like to estimate the latent strength WT star, because these strengths are defined on the continuum, right? They're defined everywhere on 0, 1. The data is given to us on a grid, but the strengths are defined on a continuum. So we would like to estimate this latent strength. So we would like to estimate between grid points. Just conceptually, this problem is actually just a non-parametric regression problem in disguise. In a non-parametric regression problem, you have an unknown function f, which belongs to some non-parametric class, and you're given values of the function in the form of signal plus noise on a grid. And then you have all these classical results for estimation. This problem can actually be reformulated in that way, but your data is not given to you as signal plus noise as we know it. You have a vector valued function, which is this WT star, and you're given pairwise information about WT stars in the form of these Bernoulli comparisons. If you think about it, it's just that, but so you have this pairwise information about this your ground truth function WT star, which is a vector valued function. So your data model is not linear. I mean, it's not signal plus noise. It's really, it's really this pairwise information about your components of this vector valued function, noisy pairwise information about the vector valued function that is given to you over time. Okay, it's important to have this perspective in mind because that's what's happening. But once we recognize that it's just a non-parametric problem in disguise, one might hope to leverage the same tools as what we know, what we use in non-parametric estimation. And since we have Lipschitz smoothness, we can actually just do a kernel, something like a kernel smoothing with a rectangular window. So we can just do this nearest neighbor estimation, okay, which is optimal for Lipschitz functions. And the idea is very simple, and it's the following. So if you want to estimate at any time point t, which is marked by this x, make a delta neighborhood for some choice of delta. Consider a delta neighborhood of t, denoted by calligraphic and delta t. And then in this neighborhood, you just simply aggregate your data. So you form the union graph G delta, which is the union of all the edges of all the graphs here. Okay, the vertex set is the same, but just take the union of all the edges of the graphs appearing in this window, make a single graph G delta T, and then you apply any static method to the union graph on the averaged observations in this neighborhood. So you make a union graph, and then for the union graph, for each edge appearing in the union graph, you simply average the observations appearing in this window, and you apply any static method. And in our case, we will apply rank centrality. The main point is how to choose delta here to balance the bias variance trade-off. So this is what we do. So we make a delta neighborhood, right, which is formally given by this, just this window, and make a union graph. So take the union of all the edges of all the graphs appearing in that window. And then for each edge in this union graph, you identify for each ij at which time points that ij was appearing in that neighborhood window, and then take the average of all the times this ij was appearing. So take the average of all the pairwise information, make y bar ij, and then we apply rank centrality on this. So just construct a random walk on the union graph using the averaged observations. And the same philosophy applies. We would expect that the stationary distribution of this random walk might be close to pi star, which is this normalized WT star, but provided that your delta is chosen carefully. So delta, of course, has to be chosen carefully to balance the bias variance errors, but also delta has to be chosen in order to ensure that your union graph is at least connected, right? Otherwise, none of this would make sense. So your delta, if it's too small, then you would have a large variance and your union graph might be disconnected. If delta is large, then you would have a large bias. Okay, so you need to have also these considerations of the union graph being connected in your choice of delta. So you have to take into account all these things. Yeah, but that's really the philosophy of what we are doing. And now it remains to choose delta to achieve all these goals and to get the right rate as a function of the number of grid points t. And this is what we do. So we have these results for Erdős Schrödinger graphs. So suppose you have a sequence of Erdős Schrödinger graphs, which need not have the same parameter. So they have parameter p of t prime. And assume for simplicity that the minimum of all these p of t primes is greater than 0, so p min. But these graphs need not be connected. So all of them could be highly disconnected. It doesn't matter. If you choose delta in this manner, as a function of t, n, the Lipschitz constant m, and p min, then it turns out that if t is suitably large, so if t is some function of n, I think it was n log n or n squared, I think, then with high probability, you have these L2 error bounds. And the important thing to note here is that you have a mixture of the non-parametric rate, which is t to the 1/3, and the parametric rate appearing. For example, if the Lipschitz constant was 0, then your error would go to 0 at the parametric rate 1 over square root t. But if the Lipschitz constant was actually like a non-zero constant, then the blue term will take over for t large enough. So your error would go to 0 at the non-parametric rate t to the 1/3. And in fact, this 1/3 is not artificial. This t to the 1/3 matches the rate for pointwise estimation of Lipschitz functions from t noisy samples. So I mean, this is really what one would expect. So this t to the 1/3 cannot be improved. So this is the right rate in terms of t. So what it says is that as you have more and more grid points, if you have more and more temporal data, you can do better and better for pointwise estimation, and your error goes to 0 at this rate. And this result applies even if all your graphs are highly disconnected, they're very sparse, disconnected, it doesn't matter. Right? And you can see how the delta is typically going to be little o of t. I mean, if m is non-zero, for t large enough, the first term in the minimum will dominate. So your window size needs to be of the order t to the 2/3 to get this right rate, which what we know from non-parametric regression. And as a sanity check, if your Lipschitz constant was 0, so then your delta would just be t, which makes sense because then you just average everything. So all these things are non-asymptotic, and you can plug in all these constants. And similarly, you can show an L infinity rate. So again, in the same setting, you have the same type of L infinity rate, but with a log n factor appearing, and the error goes to 0 at the rate t to the 1/3. And yes, I mean, the proof technique is really, we just followed the technique from this paper of Chen. So to derive these L infinity bounds, they use this recent technique, this leave one out technique, which is being used a lot for L infinity error analysis for spectral methods, and we kind of use the same thing, but there are technicalities involved because of having this union graph G delta. For these L2 error bounds, I should mention that, here we again follow the technique of Chen, and they had this Davis-Kahan type theorem for perturbation of stationary distributions of Markov chains. So we kind of used that. So that was the idea. And then there are technicalities involved due to the different problem setting. Is there any question from so far? Okay. So what we've seen is that if you have this local smoothness assumption, this Lipschitz smoothness, you can actually get these pointwise rates, and the pointwise error goes to 0. And again, I should mention that if you can estimate the latent strength vector at time t, then you can recover, if you drive the error to be sufficiently small, then you can recover the latent ranking at time t, okay? So rank recovery follows like that. So local smoothness implies pointwise recovery. But can we have okay, what if you don't have local smoothness, but you have a global smoothness assumption? And this brings me to the second part, which is translation synchronization. So now assume that you have a latent strength vector, which I will denote by Z star now. Okay, and it can take negative values as well. So it's a latent strength vector. And we have a comparison graph, just a single comparison graph. And now for each edge, we are given the pairwise difference between the latent strength Ci star minus Zj star, plus some noise, which we assume to be 0 mean subgaussian noise. Okay. So it's a different model than the BTL, but it's still related to it. So given this pairwise data Yij for all ij's in the edge set, the goal is to estimate Z star. And again, this problem only makes sense. You can only do meaningful estimation if G is connected. Okay. And this has applications in synchronization of distributed networks and also in ranking, actually, because this model that I've written here, it can be viewed as a first order Taylor approximation of the BTL model. Almost like that, not with 0 mean noise, but with some Taylor noise. But you can, if you have a BTL model, you can just write down a Taylor expansion and arrive at something like, well, similar to this. So it's not completely arbitrary, where the strength Zi star would be the logarithm of Wi star. where WI stars are positive. So it's related to the BTL model. And this has been studied, I mean, quite extensively with L2 and L infinity error bounds known. But we wanted to study this in the dynamic setting. So again, what we consider is the following. So we again have the continuum 0, 1, and we have a grid calligraphic T of size T plus 1. And at each grid point, we have a latent strength vector ZT star, and we have a sequence of graphs GT, okay, over the grid points. And at each grid point, we are given this pairwise information. So ZT star I minus ZT star J corrupted with some centered noise. So something simple. And the goal is to estimate the ZT stars over all the grid points. Okay, so I'm just going to focus on the grid recovery here. So it's a discrete, so just focus on the discrete recovery problem for the discrete set of points. Now here each ZT star has to be, we need again some kind of identifiability condition for the ZT stars to have a meaningful problem, because once you're given these pairwise differences, note that if I add a global offset to my strength vector, nothing changes here. So I lose 1 degree of freedom whenever you have pairwise comparisons of this form. So we can only recover ZT stars up to some condition. And okay, so you assume that each ZT star is centered, but you could have other conditions as well. So just to take care of this identifiability business. So each ZT star is centered. And typically the individual graphs need not be necessarily connected as before, okay, need not be connected. But now we need some assumption on how the model evolves with time. So how do these ZT stars evolve with time? And here we consider this weaker smoothness condition, which is not local, but global. So what this assumption essentially says is that the Z stars, the successive difference of Z stars with respect to this norm, L2 norm, for example, it is bounded by ST. Okay, so if you denote C to be the edge incidence matrix of the complete graph, what it says is that the successive differences, the vector of pairwise comparisons at time k is not different from the vector of latent pairwise comparisons at time k plus 1. Okay, but you can actually ignore the C transpose here and just look at it in the following way, that the norm square of ZK star minus ZK plus 1 star, the summation over K is bounded by ST. So it's like a quadratic variation assumption on your signal, nothing else. Okay, and in some sense, the fact that we have these successive differences might lead you to consider that we have an underlying path graph on the set of T vertices, and that's actually the case. So the assumption is that the strength differences do not change too quickly on average. That's the key point. So it's a global assumption, which means actually that CK stars do not change quickly on average. The interesting regime here would be that ST, when ST is little o of T, because clearly if your ZK stars are bounded, I can always bound this by something linear in T, right? The interesting case is when ST grows sublinearly in T. That's when we hope to see something interesting. So the goal would be to estimate jointly all these strength vectors. So let's denote them by Z star by stacking them column wise to get this huge vector, Z0 star, ZT star. So my goal is to estimate Z star. And I'll do this in the L2 norm. I'll show this in the L2 norm, which essentially means jointly recovering all these latent strengths. And it's useful to note that this condition that I've written here can be written in a more compact manner using the smoothness operator E. So this condition essentially says that this norm square of E times Z star is upper bounded by ST. And E is a smoothness operator that actually is the Kronecker product of the Laplacian of the path graph on T vertices and something else. So it's so the path graph, the properties of the Laplacian of the path graph will play a role in the analysis. So we have two estimators here. The first one was the natural penalized least squares estimator, right? So you have the data fidelity term plus this regularizing parameter lambda times this smoothness penalty. Because we know the original signal is smooth, with respect to the operator E. So we add this as a penalty. And the goal would be to estimate Z hat. And the choice of lambda here is important, obviously, because you want to choose lambda to be not too large or not too small. And it should achieve the bias variance trade-off as usual. And to do that, the spectrum of the operator E plays a key role. Okay, that's the key point in the analysis. The second estimator that we considered is a bit different, and it's motivated by this Laplacian eigenmaps estimator that people consider for denoising smooth signals on a graph. So this estimator is the following. So you solve locally for at each time point, find the minimum L2 norm solution of this linear system. Okay, so find the minimum L2 norm least square solution of this linear system, because it's not going to be unique typically, right? So once you get these local solutions, you stack them to get this intermediate estimate Z check. And now you enforce the smoothness by projecting Z check onto the span of the smallest eigenvectors of your smoothness operator E transpose E. Okay, and it turns out that you should project onto the smallest T times square root tau eigenvectors of this operator E transpose E, right?
Sorry, can you just remind me what is E?
Sorry?
Can you just remind me what E was?
Yes, E is here. So E is really the smoothness operator that is just a compact way of writing the smoothness condition. In fact, E transpose E is the Kronecker product of the Laplacian of the path graph on T vertices and maybe the Laplacian of the complete graph on N vertices, if I remember. So something like that. So it's just a smoothness operator.
Okay, but it's known, right? It's given by the graph, right?
Yes, I mean, this smoothness operator really depends on this. I mean, this condition here. So it depends on C, I mean, it depends on C, and it also depends on the Laplacian of the path graph, right? Because this thing can be written as a quadratic form on the Laplacian on the path graph.
Okay, thanks.
Intuitively, so. I mean, this condition intuitively another. So what this means is that if you have such a bound on your quadratic form, it means that your Z star is really lying close to the space spanned by the smallest eigenvectors of E transpose E intuitively, right? I mean, this is what it means. So if you have such a bound on your quadratic form, it means a Z star is not exactly, but approximately lying close to the space spanned by the smallest eigenvectors of E transpose E. And what the smallest means is actually going to be defined by how small ST is. So it's something like that. So indeed, to incorporate that, if you solve locally this least squares problem and you stack your solutions, then it's very natural to just project them onto the span of the smallest eigenvectors of E transpose E. But just how many eigenvectors should you take when you project them? I mean, you need the bias variance trade-off, right? So it turns out that if you project onto the T square root tau smallest eigenvectors, then it's the right thing to do. And then it remains to choose tau to balance the bias variance trade-off, which will happen later. So again, in the analysis, the spectrum of this operator E plays a key role. In particular, the spectrum of this Laplacian of the path graph. So we had these two things. And then we have these L2 error bounds for recovering this big vector of latent strength C star. And I mean, unfortunately, the results we could prove require each individual graph to be connected. And because there are technical problems that appear, which we just couldn't resolve. So that's like an open question to address. But anyway, so suppose each graph GT is connected for each grid point, okay? Then if you choose lambda in this manner, so sigma is the noise, sigma to the 4/5 and T over ST to the 2/5, okay? Then with high prob, so that's this probability 1 minus delta, your L2 error is bounded by this quantity. So how does this error scale with T? Now, clearly ST is always bounded by T. So this right-hand side is always at most T up to constants. But as I said, the interesting regime is when ST is sublinear in T, so it's little o of T, in which case this right-hand side will be little o of T, which actually means, if it is little o of T, that if you look at the mean square error, right? So the average error over the time points, it goes to 0 as T goes to infinity if your smoothness is little o of T, and so it's like a weak consistency result. So as you have more and more time points, your error goes to 0. So you would still do better than what you would do if you were to just estimate at one time point using the data at that time point, even if your graph is connected, as I said. And actually the problem we had is that if the graphs are very sparse and disconnected, there is some problem that appears in characterizing the spectrum of the sum of two symmetric matrices, and it's very challenging and it's very hard to characterize that. So we couldn't find a way around it. So it's really needed for technical reasons, but in the experiments, it really works even if you have individual graphs as sparse. And the other bound is for the projection method, which says that if you choose the number of eigenvectors tau is of this order, then your error bound is of this form. And in fact, these exponents are a bit different from what I had here. And I claim that these exponents are actually optimal based on what we know about denoising signals on a smooth signals on a graph. So this 2 by 3 and 1 by 3, so this dependence on T is actually, I believe, optimal. And in particular, if ST is of the order 1 over T, then my L2 error is order T to the 1/3, which matches the rate for estimation of Lipschitz functions over a regular grid. Because if I have a Lipschitz function, then it will satisfy the smoothness condition with 1 over T parameter, with 1 over T parameter, 1 over T scaling, and I would arrive at this rate. So as a sanity check, it matches this rate for estimating Lipschitz functions globally over a regular grid. And a similar rate is actually possible for this least squares estimator, so this 2/3 rate, but with a with an additional non-intuitive technical assumption. So I don't want to mention that. So this rate that we have is actually worse than the rate that we have for the projection method, but both of them need the individual graphs to be connected for technical reasons. That was pretty much it for this. So the main take-home message is global smoothness implies a weaker, you have a weaker smoothness assumption, so you get a weaker recovery condition. So it's a global recovery condition. And just to show a couple of plots, so we had these plots, I mean, for this dynamic, maybe BTL model, yes, for a graph with 100 vertices, and all the graphs are Erdős-Rényi with probability P chosen randomly in this interval. And the graphs can be disconnected, but the union graph was connected in the experiments. And we can compare our 3 estimators with the Emily estimator, which was proposed by Bong recently. The Emily seems to be a bit worse, but I should say that it doesn't mean that it's worse in general. I think it was just a case of choosing the wrong, maybe a wrong hyperparameter tuning. So I would not claim that this green Emily is really worse than what we're doing. It's just a wrong hyperparameter tuning. Important thing is that the methods really go to 0. The average error goes to 0 with T. And we had something like this for the dynamic transync model for different choices of smoothness. And you can see that the error goes to 0. And here we chose the graphs in a manner such that the graphs are disconnected at each T. But as you can see, the error goes to 0. So yeah, it's that's something that has to be resolved for these methods. And just to conclude, so I mean, I presented these 2 models, the dynamic BTL model, which had a local Lipschitz assumption, and we derived pointwise error bounds. And we had this dynamic transync model where we had a global smoothness assumption, and we got weaker mean square error bounds for recovering the latent signals. And in both cases, the error vanishes as the grid size increases. This is something what we saw. So, and future research, I mean, obviously we had independent observations over time. I mean, information was shared over time in the sense of the models being smoothly evolving, but I mean, clearly it's interesting to have statistical dependence over time. So that's important. We just did this as a first step. I mean, the bigger picture is this project that I've been working on. So this was part of that, which is about learning dynamical processes over dynamical networks. And this is something I'm really interested in and working on these days. Yeah, so this was really a part of that project. And just as a small advertisement, I might have multiple PhD and postdoc positions from next year in case someone is interested. But thank you. I have references here.
Okay, thank you very much. That was really a very nice talk. I will just stop the recording and we can ask any questions